In addition to the main components described in the theory section, the refrigeration system illustrated here includes all the control devices needed for normal operation. We will now examine how these devices operate. In the theory section, we learned that when the system is off, the refrigerant is waiting in the condenser. For it to enter the evaporator, the solenoid valve must first open. The signal to open the valve comes from the room thermostat, which closes an electrical contact when the room temperature is higher than the temperature set by the occupants. Some systems have a timer that turns the system off when the building is unoccupied. Others have an outside thermostat that prevents the refrigeration system from coming on when the outside temperature is too cold. Therefore, the compressor will only start up if the timer and outside thermostat allow it to do so. The liquid refrigerant starts to flow towards the expansion valve. At this point, it is at high pressure, with the pressure being close to the pressure it had in the condenser. You can see the refrigerant flowing through the sight glass. As it flows, the refrigerant is filtered to remove possible residues or metal particles. The moisture it may have absorbed during maintenance is also removed by the same filter dryer. The liquid refrigerant at high pressure thus arrives at the expansion valve, which is set to lower the pressure to obtain the temperature required in the evaporator. The expansion valve is also a flow control valve. It controls the amount of refrigerant that enters the evaporator depending on the evaporation rate. The evaporation rate varies with the amount of air to be cooled, the air temperature, and the degree of humidity in this air as it passes through the evaporator. The expansion valve measures the evaporation rate by means of a bulb located at the evaporator outlet. This bulb measures the amount of superheat of the refrigerant. When the degrees of superheat increase, it means that the refrigerant is evaporating faster than it enters the evaporator. The expansion valve then opens more to increase the flow. However, if the number of degrees of superheat drops, it means that the evaporator is being flooded with liquid refrigerant. The expansion valve then reduces the flow until the superheat returns to the desired range, usually 8 to 12 degrees Fahrenheit for thermostatic expansion valves. Electronic expansion valves operate with a superheat range of 4 to 6 degrees Fahrenheit. You will notice that the expansion valve also receives a pressure signal measured at the evaporator outlet. This signal allows the expansion valve to adjust to the pressure drop in the refrigerant as it goes through the evaporator. This pressure drop lowers the evaporation temperature slightly and could give a false superheat reading if it were not compensated for. Under normal operating conditions, the level of liquid refrigerant stabilizes in the evaporator so that the flow of liquid is proportional to the amount of heat to be absorbed. The compressor starts up at the same time as the solenoid valve opens. Compressor startup is also regulated by a pressure control that measures the minimum pressure that needs to be present at the compressor suction inlet. This is the cut-in pressure. This pressure is usually reached when the compressor starts up because the remaining refrigerant in the evaporator has evaporated while the compressor was off. This control is useful to prevent the compressor from starting if there is not enough refrigerant coming out of the evaporator. The compressor can be shut off by one of the three following controls. The first is the room thermostat. This thermostat shuts off the compressor if the ambient temperature is lower than the set point temperature. The second is the pressure control that measures the minimum required pressure at the suction inlet. This means that if too little refrigerant is coming from the evaporator, the compressor will be stopped. This is the cutout pressure. And the third is the pressure control that measures the pressure at the discharge outlet. It is called the high pressure cutout. When the discharge pressure is too high, the compressor shuts down. This may indicate that there is an operating problem that could damage the mechanical components. Under normal operating conditions, the compressor runs as long as the thermostat has not reached the desired room temperature. The gaseous refrigerant which is drawn in from the evaporator is compressed to a high pressure. The refrigerant temperature then rises instantly with the increase in pressure, and the refrigerant flows towards the condenser. In order to try to adapt to the variable flow of the refrigerant arriving at the compressor, some systems use multiple compressors. As the flow of refrigerant increases, the suction pressure increases, which in turn allows a larger number of compressors to start up. The condenser receives the gaseous refrigerant at high pressure and high temperature from the compressor. The function of the condenser is to condense the refrigerant in order to then return it to the evaporator. The compressor and the condenser fans operate simultaneously. It is the outside air that absorbs the condensation heat. The function of the inverted U-trap located at the condenser inlet is to reduce the hammer effect caused by the sudden arrival of a mass of refrigerant in the condenser. This usually occurs when the compressor starts up. The inverted U-trap also holds back the liquid refrigerant and prevents it from returning to the compressor when the compressor is off. The refrigerant reaches the bottom of the condenser as a liquid at high pressure and high temperature. As soon as this happens, it again passes through the expansion valve to re-enter the evaporator at the required temperature and pressure. The refrigeration cycle continues to operate as long as the room thermostat indicates that there is a need for cooling.